In lecture 6, we are going to study light absorption, which is one of the targets for us. And in the previous 2 lectures, we studied the two transitions of rotational energy state and a vibrational energy state. And I mentioned that these transitions affect the light absorption, and they could be answered here. So here's the process. So just simply we are going to think about some of the molecules like benzene here, and then light is propagating towards this benzene, right? And benzene has light absorption around the wavelengths around 260 nanometer. On the other hand, the size of the benzene is 25 square angstrom. So it's compared with the size of the molecule with wavelengths. The molecules are quite small. Actually, it's a long wave is coming to a very small, very tiny object. That's actual image you have when the light absorption happens. Okay. And first, let's think about how the light absorption happens. The necessary time for light absorption is at least one single wavelength of light must pass through the molecule, right? Because for each molecule, this molecule needs to know what kind of light is coming to this molecule, and what kind of light means the wavelengths of the light. So at least one of the wavelengths must go through the molecule. Otherwise, this molecule cannot absorb the light. So based on this consideration, that means that at least for the light absorption, the one single wavelength, meaning in this case 260 nanometer, and it propagates with the velocity of light. It's equal to 0.8 10 to the minus 15, meaning 0.8 femtosecond. It's around 1 femtosecond, right? So just remember that at least 1 femtosecond is necessary for light absorption, roughly. And then the next step we have to understand is one of the most important principle for the light absorption, called Franck-Condon principle, right? Franck-Condon principle is one of the key fundamental of the light absorption. And to understand the Franck-Condon principle, first you have to understand the reaction coordinate, which means reaction coordinate is the relation between the energy state versus some molecular parameters such as bond lengths, bond angles, and so on. So just simply think about the reaction coordinate for diatomic molecules like this, and take this distance r. So it's like R is taken for the horizontal axis, and this is energy. Then you could think like for ground state and excited state. So meaning that this molecule, as we studied in the vibrational transition, there is some equilibrium distance for the molecules. And also this distance could be changed. And then this one is the ground state. This one is, for example, excited state. And the excited state, the equilibrium position is actually different from the ground state. And the other things you can know is there's a vibration state is on this electronic state like this. So what it means, the thing is centered at the equilibrium state, that this diatomic distance could be changed by different distance like this. So it means the distance between two atoms can be changed, and then the energy can be changed. This is the oscillation, meaning the vibrational energy level. So centered at Re, this molecule could change the distance, and due to the minimum energy, it can oscillate. This is vibrational energy. And for simplicity, we frequently show this energy level like this is 0 as 1. But we know that there are additional vibrational energy level on like this. And simplified one. Simplified expression is like this, but actual energy level for this molecule is actually explained by this reaction coordinate graph. So, and what is important in the Frank-Condon principle is the nuclear atom position cannot move during the electronic transition, meaning the light absorption. So the position change of nuclear, meaning atom, is induced by the vibration or oscillation, vibration or rotation of the motion. But during the light absorption, this motion cannot be possible because this light absorption itself is on the order of 1 femsecond, and there's no time to change the position. This is what Frank-Condon principle says. So let's briefly calculate how long does it take for the oscillation time of OH stretching mode, which is about 3000 Kaiser. So please stop the video and please think about how long does it take. Okay, then the time is, since the in frequency it's about times So it's a 3000 Kaiser, and it can be coupled with the light, meaning the light velocity given by centimeter per second is equal to something like, it's a 3 times 10 to the 10, and it's correspond to 90 times 10 to the 12 hertz, meaning equal 1/2. So this frequency is equal to around 10 femtosecond. So which is longer than 1 femtosecond, but yeah, it's not so small. But obviously, during the motion of the atoms, the light absorption is much faster. So here's the things that for understanding the Frank quantum principle. And as I mentioned, here's a reaction coordinate for diatomic molecules. Right. So this axis means the distance between two atoms. So for ground state and excited state, the distance for equilibrium are different. And at each centered at the equilibrium position, this can oscillate due to if some extra energy is given to this molecule. That is a vibrational oscillation. And what the Frank quantum principle mentioned is this kind of, the distance change cannot be possible if during the light absorption, meaning the electronic transition, because the electronic transition is very fast. That means based on the Frank quantum principle, most of the vibrational energy is usually the ground state at room temperature. And from this ground state of vibrational state, when the light is absorbed, this the ground state is going up to the excited state, and then the Frank quantum principle mentioned it cannot be possible like this, because this is going to change the distance of the atoms, but there's no time for this. So what happens here is the molecules with the distance of RE is keeping this RE distance going up to this excited state. And so this is not the equilibrium position of the excited state. That's why it could start oscillate. So in a sense, the excited ground state of the excited state is formed, and that's why it could induce the oscillation. So this is what happened during the light absorption. Then, as a next step,